Okay, welcome back. So last time we started setting up the integral to calculate the electric field of a long straight wire of charge density lambda. And we ended with this expression here. And this is what we got by saying that dE is k dq over r squared cosine theta. Now the next step is we're going to have to do a little bit of rewriting here. And one thing that we want to do is to write this as the integral of k, but instead of dq, we're going to use lambda dx. That's going to be over r squared times the cosine of theta. Now at this point, we're going to need to carry out this integral. And the problem is that we have basically three variables. We have dx, we have theta, and we have r, all of which are not related to each other very nicely. So if we recognize that this distance here is x, and we're given this distance here of y, one thing we could do, and by the way, there's multiple ways to solve this problem, but one way, which is kind of pretty, is to say the tangent of theta in this case is x over y. And that means that x is equal to y tangent theta. Now if we do implicit differentiation on each side, we can see that dx is equal to y, which is a constant, times the secant squared of theta d theta. Oops. Okay, and that's going to get substituted in for dx over here in a moment. But we also need to take care of r. And we might notice here that the cosine, so if this is r, we might notice that the cosine of theta is y over r, but the secant of theta is r over y, which means that r is equal to y secant theta. And the reason why we do this is that now if we square each side, r squared is equal to y squared secant theta. So now we have two substitutions that we're going to make. We're going to take this one here and plug it in for r squared. And I'm going to erase that because we don't need that. And I'm also going to plug in that dx is y secant squared d theta. So now our integral is going to be a lot nicer. It's going to be k lambda, and then dx is going to be y secant squared theta cosine theta d theta. We'll just switch that order. And r squared is going to be y squared secant squared theta. And that's beautiful because we get rid of a y and we get rid of secant squared. So now what we're left with is the integral of k lambda over y of cosine theta d theta. Now, what are the limits on this integral? If you look at our angle theta, that is measured from the vertical. So if this is an infinite wire, and we're talking about a piece over here that is basically at infinity, the angle is going to trend to basically pi over 2. Okay, so our integral is actually going to be from negative pi over 2 on the left side to positive pi over 2 on the right. That'll be the limits for our angle. And we know that integral pretty well. It's just k lambda over y. And the integral of cosine is sine. And that's from pi over 2 to negative pi over 2 or vice versa. And so our final answer here, let's get back to our orange color. Final answer for the electric field is going to be k lambda over y times 2. And that's it. Because when we plug in pi over 2 for sine theta, we get 1. And when we subtract the sine of negative pi over 2, we'll subtract a negative 1. So we simply get 2 k lambda over y. And this is a really remarkable result because there's no dependence in this on where you are on the wire. It's just k lambda over y. And you can check the units to make sure that it gives the correct units for electric field, but it does. Okay, so let's do another example. Now, we're going to find the electric field for a ring of radius r which has charge q. Now, the setup for this is very similar. This ring is going to have a linear density lambda, which is dq ds. So now instead of x or y, we're going to say that a tiny bit right here has dq and a length of ds. And we're going to try to integrate going around in a circle. Okay? Now if I think about the field from this tiny little piece, it's going to be going this way. This will be dE. And that of course has a dEx and a dEy. And for the same reason as before, if we call this angle theta, and this is theta, the dEy's will cancel. So that means that dEx, which is equal to dE cosine theta, that's all we want. So the electric field is going to be the integral of dE cosine theta. Now remember that dE is k dq over r squared cosine theta. And again, we need to convert this so that we have all the same variable. Okay? So one thing that we're going to do with dq is we can write that dq is equal to lambda ds. So that means that this field is going to be k and then lambda ds. The other thing that we can do here is, well, we can do a couple things. But one thing is we can note that the distance little r is actually related to the radius big R and the distance x. So it's just Pythagorean theorem. Little r squared is equal to big R squared plus x squared. So this will be big R squared plus x squared. And the cosine of theta, if you think about it, the cosine of theta will be x over r. So we have x, and then little r is equal to the square root of r squared plus x squared. So we'll have the square root of r squared plus x squared. So that simplifies a little bit, and we'll have the integral of k lambda x over r squared plus x squared to the 3/2, and then we have a ds. Okay? Now, here's the thing. As we go around this ring, nothing in the parentheses here is changing. X is always constant, big R is constant, k and lambda are constants. The only thing that changes, well, is nothing. So this means that we can write the electric field as k lambda x over r squared plus x squared to the 3/2 times the integral of ds. Now the integral of ds is just equal to 2 pi big R, the radius of the ring. So that gives us an expression here for the electric field of k lambda x times 2 pi r all over r squared plus x squared to the 3/2. Now there's one more thing that we can do. Remember that sometimes we can write the density not in terms of just dq or ds, but we can write it in terms of the total charge over the total length. So that's 2 pi r. So from this, you can notice, I'll write it here, that Q is lambda 2 pi big R. And if you see here, here's lambda, here's 2 pi r. Those put together are big Q, so we can simplify our electric field to K big Q x over big R squared plus x squared to the 3/2. And that's going to be our final answer for the electric field. Now, there's one more thing that we want to check for this. Okay? Well, two things. First of all, we want to check when x is equal to 0. So in other words, if we are in the center of the ring, well, the electric field is going to be 0 because we have an x in the numerator here. And that makes sense because if you're in the center of the ring, all the contributions from all the pieces cancel. The top of the ring gets canceled by the bottom. This piece right here gets canceled by this piece. And so in the center of the ring, there's no field. Now the other thing we want to check is what happens when x is much, much larger. That doesn't even exist in math, but much, much larger than r. Well, in this case, you can pretty much ignore the big R squared down here in the numerator, and it's just basically x squared to the 3/2. But that's just x cubed. So we get kqx over x cubed, which is kq over x squared. So this is the expression for a point particle. So in other words, if you envision that you're holding up this ring, think about an actual ring, and then you run a mile away. The ring looks like a point because it's so far away. So this is one way that we can check our electric field expressions to make sure that we're coming up with reasonable answers. Okay, let's see if we can cram in one more example in this video. And okay, sorry about that. We had to skip ahead one, but let's see if we can quickly do this for a disk. So this shows a ring, but we really have a disk here of radius r and charge q. And we're going to pick right up where we left off. And earlier, we found that a ring had a field of qx over big R squared plus x squared to the 3/2. Okay, so now the trick is, if we want to find a disk is just made up of a bunch of concentric rings. So this ring here will have charge dq, and it's going to not have length, but it will have area dA. And then what we're going to need to do is this will cause a field of dE, which we already know will just point in the x direction, and we're just going to have to take the integral of all of the dE's. And that integral is going to have to go from the center of the ring until little r is equal to big R. Okay? So dE in this case will be the field of a ring, and we're going to have to put a dq in there. So just to write that out, we're going to go from 0 to r of kx dq over, now it's not going to be big R squared, it's going to be little r squared plus x squared to the 3/2. Now in this case, little r is how far out we're going in the disk. Okay, it's not the distance from a point on the disk to point P like earlier, it's actually the radial distance along the radius of the disk. Okay, now we're going to have to say that we have a surface charge density here. Okay, so sigma will be dq over dA. Okay, so that means that dq will be equal to sigma dA. But the question is, what's dA? Well, let's go to our orange pen. Okay, well, we're talking about a ring, and this ring has a width of dr, and it's got a circumference of 2 pi r. So that means that dA is actually going to be equal to 2 pi r dr. So this is basically the length of a ring, and this is the width. You multiply those and you get the area. Okay, so what do we do with this? This means that dq is going to turn into sigma times 2 pi r dr. We take that and we plop that into our expression. So this is our expression for the electric field. We will have the integral from 0 to big R of kx times sigma 2 pi r dr, and that's all over little r squared plus x squared to the 3/2. Let's clean that up a little bit. Let's take all our constants out. It's still from 0 to r, but now what's going to be constant? Well, everything basically, k, x, sigma, and then pi. Okay? Now, it turns out that to make life a little bit easier, we want to leave the 2 up there along with the r, and you'll see why in a moment. So r squared plus x squared to the 3/2 dr. And we're just going to use u substitution. We're going to say that u is equal to r squared plus x squared, which means that du is 2r dr. Remember, x is constant. And that's why we left the 2r up here. So that means that our integral turns into k, x, sigma, pi, and we have different limits. When little r is 0, u is x squared, and when little r is equal to big R, it's big R squared plus x squared. Then we're going to have 2r dr is basically du, and that's going to be over u to the 3/2. Now we know how to integrate that. We have our constants, and that's just going to turn into u to the -1/2 evaluated from x squared to r squared plus x squared. Now we just plug and chug, and what we're going to end up with is that the electric field is 2 pi k sigma x, and sorry, I forgot to divide this by -1/2. My bad. That's where our 2 is going to come from here. And I'm going to write it this way, that we're going to end up with 1 over x minus 1 over the square root of x squared plus big R squared. And that's going to be our final answer for the electric field of a disk. Now, there's one final thing that I want to point out, and that is what happens when big R gets really, really big. So, in other words, as big R goes to infinity. So that's also known as an infinite sheet. And we'll see why this is important later on. As big R goes to infinity, what happens to this expression? Well, basically, the 1 over root x squared plus r squared goes to 0. And I'm just going to lightly show that by just canceling that out. And that means that the electric field for an infinite sheet is going to be 2 pi k sigma. And that's it. Okay? The x's are going to cancel because we have this x right here canceling with 1 over x right here, because this term has gone to 0. Now remember that k is 1 over 4 pi epsilon naught. This means that the electric field, I have to write over here, is going to turn into sigma over 2 epsilon naught. And this is for when r is going to infinity. This is an extremely important result, and we're going to see how to get this a little bit easier in a later video. So we're already up to 20 minutes, so we're going to have to call this one quits. I will see you next time.